Hello and welcome to the world of real numbers. Real numbers are fundamental mathematical concepts that include all rational, irrational numbers, all fraction, integers, all of them are included under the category of real numbers. Real number line basically depicts all real numbers extending from minus infinity on the left to plus infinity on the right with zero at the center. In between the 0 and plus infinity, we mark the integers, positive integers, and on the left hand side, we mark the negative integers. Now, if we talk about the integers, in between any two of these integers, there are infinite, rational, and irrational numbers. Now, in this channel, I'll be talking about real numbers with the perspective of class 10 CBSE syllabus. So, whatever we do will be in tune with class 10 CBSE syllabus. Now, real numbers basically are bifurcated into two major subheadings or two major categories, rational numbers and irrational numbers. Rational numbers can further be subdivided as non-integer rational numbers and integer z. Now, from the integers, if we remove the negative integers, we are left with whole numbers w. And from the whole numbers w, if we remove 0, we are left with natural numbers n. Irrational numbers are of the form root 2, root 3, pi, all these are irrational numbers. Now, how do we differentiate between rational and irrational numbers? What are the basic bifurcation rules for rational and irrational numbers? Let's try to understand that. All rational numbers can be represented in the form of p by q, where p and q are any integers. They can be positive, negative, or they can be positive or negative, and q is never equal to 0. So that has to be kept in mind. Q can never be equal to 0. But irrational numbers cannot be represented in this format. Second basic difference between rational and irrational numbers is the decimal expansion. The decimal expansion of rational numbers will be of the form terminating decimal expansion, like if I write 4.5 or 4.75. These are terminating decimal expansions. You can have 2 digits, you can have 3 digits, but it terminates. That is, there is an end to this decimal expansion. And another form of decimal expansion of rational numbers will be of this form, say like 2, and then you have this 3, and 3 goes on repeating itself. So when you find a 1 digit or 2 digits or 3 digits keep on repeating themselves, this is called non-terminating but recurring decimal expansion. This is also found in rational numbers. But in the case of an irrational number, the decimal expansion will be something of this type, say 6, and you will see that you go on dividing, but it is never going to end, and neither of the digits are going to repeat themselves. So this is for irrational numbers. Now, getting back to rational numbers, now if you get a terminating decimal expansion, how do you understand that you will definitely get a terminating decimal expansion? For that, we check the denominator, that is q, or the integer q. Now, if q can be written as a product of 2 to the power m into 5 to the power n, or for some index m in n, then it is a terminating decimal expansion. Here you can also observe that m can either be 0 or n can be 0. Either of them can be 0. So if supposing m is 0, then it becomes 2 to the power 0 into 5 to the power n. So this is 5 to the power n. Similarly, if n is 0, then it becomes 2 to the power m. So if we have q in this format, then it is a terminating decimal expansion. For example, supposing if q is 8, it becomes equal to 2 to the power 3. So it's a terminating decimal expansion. Here 5 is raised to the index 0. If I take q as 10, it is 2 into 5. So obviously it is of the form 2 to the power 1 into 5 to the power 1. If I take the denominator as, let's take 25, q is 25. So this becomes 5 square. So here 2 is raised to the index 0. So whenever we get a divisor which can be written in this format, 2 to the power m into 5 to the power n, then it will definitely be a terminating decimal expansion. But sometimes what happens in the divisor in the q, if we break it up into its prime factors, you will find that apart from 2, and say 2 is being raised to a particular index m and 5 has been raised to a particular index n, and you also have say 3 and you may have 7, some other numbers, prime numbers also are present there. Even if you have one extra prime number over there and which cannot be cancelled by any term in any factor in the numerator, then definitely this will give us a non-terminating but a recurring decimal expansion. So you may have 3, you may have 7, any one of them or both of them or any number of more factors. So you will definitely then get a non-terminating but recurring decimal expansion. So if you want to identify whether it's a terminating decimal expansion, just have a look at the denominator q. And if you notice that the denominator q can be written in this format, you can easily come to the conclusion that it is of the form 2 to the power m into it is a terminating decimal expansion. So that's all of that. Now we move on to what we have to do in this chapter, Euclid's division lemma. Lemma is basically an accepted mathematical statement, and division over here is whatever we have done division in the lower classes, that is being taken care of in this. And Euclid is the Greek mathematician who compiled this Euclid's division lemma. So what basically is this lemma? Before we read the statement, let's understand what basically is this lemma and how it was compiled. Now supposing I take a small number 9 and divide it by 2. This is an improper fraction. This can be written as a mixed fraction 4 1 upon 2. So this 4 1 upon 2, from this we can get back the dividend 9 once again. How? If I take 2, that is a divisor, and multiply it with the quotient 4 and add the remainder, I'll get 9. Similarly, if I say take another number 15 and divide it by 3, I'll get here 5, only no remainder. So this also, if I take the divisor and multiply it by the quotient and I'll get the remainder 0 over here. I'll get 15, and this gives me 9. So the dividend is obtained by this divisor into quotient plus the remainder. Divisor into quotient plus the remainder. So you may notice over here that the remainder can be 0 or it can be any other number. So this has been virtually compiled in the form of Euclid's division lemma. And it talks about any positive integer. Supposing we have two positive integers a and b, then there will be two more positive integers q and r, such that a is equal to bq plus r, where r is less than b, greater than equal to 0. So r can be 0, r but has to be less than b. R is the remainder. So this is the basic statement. It says that for positive integers, a has to be greater than b, and if you divide a by b, this is the divisor, this is the quotient, this is the remainder. R has to be less than b, greater than equal to 0. So this is the statement of Euclid's division lemma. If we check from here, this is divisor into quotient plus remainder. Divisor into quotient plus remainder. So this is what has been compiled in the form of Euclid's division lemma. Now what are the applications of Euclid's division lemma? Basically, Euclid's division lemma makes it very convenient for us to find out the HCF of two big numbers. Now, of course, you can do for these big numbers also, you can approach the prime factorization method, but it will be a bit too longer. So here we take the help of Euclid's division lemma to calculate the HCF. Now the two numbers are 1, 2, 5, 7, 6. First thing that we need to do is identify the bigger number and take that as the dividend. And the smaller number becomes the divisor. So now we need to find Q and R. For finding Q and R, we divide this by 4052. And here, if you look at this 4052 carefully, 4 into 3 is 12. So, and here this is 5 and 5 into 3 is 15. So obviously it will be 3 times. So you get here 6, this is 15 and this is 1 and this is 12. So the remainder is 420. So into 3 plus 420 is the remainder. So next step, you notice over here 420 is the remainder. Alright, 4052 was the divisor. Next step, 4052, the divisor in the previous step becomes the dividend. and the remainder becomes the divisor. Now let's see 420 divides 4052 how many times. Now if you check these two numbers properly, if you take 10 times, it's definitely going to exceed and it will become 4200. So one time less, and this will give us 9 zeros, 9 twos 18, 9 fours 36. You can even check 9 into 4 36. 8 into 4 will be 32, very less. So this becomes 2. This becomes how many? This is 4. So this is 6 over here. And sorry, this is 5 here. So this is 7. And this is 9 minus 7. That is 2. So 272. So into 9 plus 272. Next step, 420 becomes the dividend, 272 becomes the divisor. So what is the remainder? 420 minus 272, that is 8. And this becomes 11 minus 7, that is 4. And this is 148. So 148 is the remainder. Next step, 272 is divided by 148. Obviously, it is 1 times. What is the remainder? 272 minus 148. This gives us 4. And this is 6 minus 4. That is 2. And this is 1. So plus 124. So every time you notice that the remainder will be less than the divisor. Next step, 148 is equal to 124 into 1. And remainder obviously will be 24. 24 is 48. Next step, 124 is the dividend and 24 is the divisor. Now 24 into 5. If you do 24 into 5, it will give you something 120. 24 into 5, and this becomes remainder is 4. Next step, 24 becomes the dividend, 4 becomes the divisor, 4 into 6, and remainder is 0. So once we get the remainder 0, we stop the division process. So this remainder, this divisor 4, which was a remainder in the previous step, all right, will be the HCF of these two numbers. So you should not confuse whether 6 will be the HCF of 4. Check out the remainder in the previous step. Remainder was 4, and so this becomes the divisor, and this divisor in the step which gave us the remainder 0, that is the HCF of these two numbers. So you see how quickly we can find out the HCF of two big numbers. If you sit to find the prime factors of these two numbers, it will take a long time. Of course, you can do it. Now, this is another application of Euclid's division lemma. Show that every positive even integer is of the form 2q. Every positive odd integer is of the form 2q plus 1. Now here, if we compare this with the Euclid's division lemma, a is equal to bq plus r, where r is less than b, greater than equal to 0. All right. Here, if I make this divisor, which is b over here, as 2 and take any positive integer a, I can write 2q plus r. Now we have seen that r has to be less than b. Here my b is 2. So r has to be less than b. So r will be either 0 or it will be 1. It can't be 2. So then this expression can take the shape of a is equal to 2q or a is equal to 2q plus 1. So we get two expressions like this. Now, all positive even integers, if you multiply any number by 2, it becomes an even integer, can be expressed in this format. And if any even integer 2q is to that we add 1, it becomes an odd integer. Let's take an example. Supposing I take 8. 8 can be written as 2 into 4 plus 0. If I take a as, say, let's take 25. So 2 into 12 plus 1. So you get a remainder 1 here. So any odd or even integer can be expressed in this format. A is equal to 2q or 2q plus 1. So this is another application of Euclid's division lemma. Now let's take some word problems based on HCF. Find the largest number which divides 320 and 457, leaving remainders 5 and 7 respectively. Now here largest number which divides. So when you are given this word divides 320 and 457, that means that number is obviously smaller than these two numbers. So you need to understand that when it is dividing, you need to find the HCF, because HCF is always less than the LCM. So you don't have to find the LCM. HCF, it's dividing these two numbers, so HCF has to be smaller than these two numbers. LCM will be greater than these two numbers, or maybe equal to the product of these two numbers if you don't have any, there is nothing common in them. So we take, for finding out these largest number which divides it, and here it's also mentioned that it is giving us a remainder 5 and 7 respectively. So respectively means from the first number you have 5 as a remainder, from the second number you have 7 as a remainder. So in order to solve it, what we need to do is remove these numbers 320 minus 5 and 457 minus 7, the remainders. So here I get 315 and here I get 450. Now we'll calculate the HCF of these two numbers. These are small numbers. You can do it by any other method, but I am taking the help of Euclid's division lemma. It will be 1 times and 450 minus 315. This will be 5 and this will be 4 minus 1, 3 and this will be 135. So 135. Next step, 315. 315 is the dividend, and 135 is the divisor into 2 times 270. So 315 minus 270 will of course be 45. So this gives us 45. So plus 45. Then 135 is equal to 45 into 3 plus 0. So 45 becomes the largest number which divides these two numbers, and when you divide 320 by 45 you get a remainder 5, and when you divide 457 by this 45 you get a remainder 7. So this is another word problem based on HCF. Now we have another word problem based on HCF. We are given here 3 sets of English, Hindi and Maths books are to be stacked subject wise, and the height of each stack is the same. The number of English books is 96, the Hindi books is 240 and the Maths books is 336. Books are of the same thickness. This is important. Calculate the number of stacks of English, Hindi and Maths books. Alright. So height of the total stack, if you are placing the books one over the other this way, whatever height you get, where you say one stack of English and another stack of Hindi, the total height of these stacks must be the same. So here what you have to keep that in mind. So in order to get the number of books in each stack and then finding out the subsequent number of stacks of each category, let's find the HCF of these numbers. So here we have 96 and 240. So again I'm taking the help of Euclid's division lemma. 96 into around 2 times, so it will give us 96 into 2 is 12, 192. So what is the remainder? 40 plus 8, that is 48. So into 2 plus 48. Then 96 is equal to 48 into 2 plus 0. So 48 is the HCF. Similarly, if I take this 48 and check out with 336, find out the HCF of these two numbers. 48 into, you get 7 times 7, 8, 56, you get 336, you get the remainder 0. So 48 is the HCF of these three numbers. Now, in order to find out the number of stacks of each variety, if I take 96 and divide by 48, now I know that I have to keep 48 books in one stack, whether it is of English or Hindi or Maths. So 48, this will give me 2 stacks. 240, this will give me 5 stacks. And 336, 548, this will give me 7 stacks. So these are the number of stacks of each variety that need to be made. Let's take another question. 140 cartons of Coke cans and 90 cartons of Pepsi cans are to be stored in a canteen. If each can is of the same height and contains cartons of the same drink, what would be the greatest number of cartons each stack would have? Greatest number of cartons each stack would have. Again, you are stacking 144 cartons and 90 cartons. One Coke is 144 cartons and Pepsi is 90 cartons. So you have to stack it so that the height of each carton, each stack is the same, and it contains the same drinks. So again, we find the HCF of these two numbers. 144 is equal to 90 into 1 plus how much? This is 44 and this becomes 54. 90 is equal to 54 into 1 and this becomes 36. Then 54 is equal to 36 into 1, this becomes 18. Then you have 36 is equal to 18 into 2 plus 0. So 18 is the maximum number of cartons you can put in one stack. And again, you can calculate the number of stacks of Cokes and Pepsi separately with the help of this HCF 18. So everywhere we are applying this Euclid's division lemma to calculate the HCF. You can see even for small numbers, you get in a jiffy the HCF of the two numbers. So of course, definitely you can do it with prime factorization. There is no stopping and nobody can restrict you from using prime factorization method. Since you're learning something new, especially when you get big numbers, it makes it very convenient. So we stop this video over here, and the next video I'll continue with fundamental theorem of arithmetic. So do log in if you like the explanation. Kindly subscribe and share the channel. Thank you.